For the Lewis structures and molecular shapes activity, we are drawing Lewis structures and drawing molecular shapes of many molecules and ions. So for the Lewis structures, our step-by-step procedure, which we also have outlined in the Chapter 8 lecture handout. First off, we figure out how many total number of valence electrons we're working with. In our example of NO3-, we have 5 for the nitrogen and 6 for each oxygen, so plus 6 times 3. Then we have a minus charge, so we're adding one more electron. So we have 24 electrons we're working with. And then we put the element in the middle that is most likely to be the central atom, and it's the one with the least electronegativity. It's the one that's only there in a quantity of 1. It's often the one written first. So we draw that in the middle, surrounded by the other atoms, which in this case is the 3 oxygens. And then we have the remaining electrons that we just put in. So we have 24 electrons to work with. We have used 6, so we still have 24 minus 6 to put around in our molecule, in this case ion. Of course, certain ones like hydrogen only want a duet. Beryllium actually only wants 4 electrons total. Boron only 6 electrons total. Otherwise, for most of the elements, they want the octet 8. Okay, so in step 4, we have the remaining pairs of electrons are used. One of 3 situations will occur, as shown in the figure below. So to satisfy the octet rule, if we have just enough electrons, then great, we're almost done. Well, we don't, because we have nitrogen with only 6 electrons, not 8. If we have not enough electrons, which is our case there, what that means is we simply don't have enough bonding. So we need to add another bond. And we're cautioned to be careful not to change the electron count. So what we have to do is take a pair of electrons, because in our diagram shown beside the rule number 3, we are showing all of our electrons, all of our valence electrons. We have to take a pair of electrons, a lone pair, and make them as a bond. Okay, the last example, though doesn't apply to us, but does apply to a lot of situations, is if we have extra electrons. Then we put an expanded octet around the central atom, which is fine if our central atom is from row 3 or higher. Okay, so for NO3-, there are not enough electrons to give the nitrogen atom an octet using lone pairs and single bonds. Therefore, to satisfy the octet rule, one lone pair on an oxygen atom, that would be the one on the right, is converted into a bonded pair. So now we have a double bond on the right between N and O. Okay, the final steps. If the structure is ionic, we enclose it in square brackets and we indicate the charge in the upper right corner. So that's what we've done. If multiple bonds are present, consider if equivalent resonance structures are possible. That is the case with NO3-. We could have the double bond on the left side or the double bond on the right side. So what we have is 3 equivalent resonance structures. And in the end, what that means is between every N, or between N and each O, we have about a 1 1/3 bond, always there simultaneously. It isn't that at one instant it's on the right, the next it's on the left, and then later is down below. It's simultaneously that we have 2 extra electrons spread throughout the whole molecule. That's what resonance ultimately means. We have another example shown for resonance, and that is with O3, with 18 valence electrons. It turns out that we have to have a multiple bond to have each O have the octet rule satisfied, and the average O single bond O bond length is 132 picometers, where pico is 10 to the minus 12. The average OO double bond length is 116 picometers. The observed bond length in O3 is 128, so it's between the two. So that supports, that experimental observation supports the fact that it's actually 1.5 bonds simultaneously always there between the central O and the attached O's. Formal charge, that is something that we don't have in the lecture handout. The formal charge on an atom is the difference between the number of valence electrons on that atom and the number of electrons assigned to that atom in the Lewis structure. And that's shown in equation 1, where assigned electrons are either lone pairs, that counts as 2 on the atom, or half of the bonding electrons. So if it's a single bond, that contributes 1 electron. If it's a double bond, that's 2 electrons, and so on. Okay, so formal charge is, and we calculate formal charge in a molecule or ion for each atom. The formal charge of the atom is its number of valence electrons minus the number of assigned electrons. So in this figure 2, for the ion NO3 minus, we have 3 possibilities. The first possibility, the triple bond on the right side. The second, the triple bond on the left side. The third situation, situation 3, we have 2 double bonds. So to decide which of those is the most likely, we determine formal charges for each atom, and the situation that's most likely is the one that has the smallest formal charges for all the atoms considered together, and where there has to be a negative charge, that it be on the most electronegative element. Okay, so calculating it for each atom, going to figure 1, N on the left, we have for N always valence number of electrons is 5. So that N on the left, we have 2, 4, 6, 7. So 5 minus 7, negative 2 for that N on the left. The N in the middle, 5 minus 1, 2, 3, 4, or plus 1. For the N on the right, we have 5 minus 1, 2, 3, 4, 5, or 0. Then we go to structure 2. The N on the left is 5 minus 1, 2, 3, 4, 5, 0. N in the middle, 5 minus 4, 1. And then the N on the right, 5 minus 1, 2, 3, 4, 5, 6, 7, negative 2. The third structure, the N on the left is 5 minus 1, 2, 3, 4, 5, 6, or negative 1. The N in the middle is 5 minus 1, 2, 3, 4, or plus 1. The N on the right is 5 minus 1, 2, 3, 4, 5, 6, or negative 1. So make sure that you understand how those are calculated and go through it and make sure you get the same answers. If there are multiple non-equivalent Lewis structures for a species, the higher contributing resonance structure, that is the most likely one, is the one that A, minimizes the formal charges. So the more zeros there are, the better. Plus 1 on 2 separate atoms is better than plus 2 on 1 atom. And B puts a negative formal charge on a more electronegative atom, and or a positive formal charge on a less electronegative atom. Also, going back up here, the net formal charge for a structure has to equal the charge of that structure. So go to structure 1. -2 plus 1 plus 0 is -1. That equals the -1 overall. Structure 2, 0 plus 1 minus 2, -1 overall equals the -1 of the ion. The last one, structure 3 plus 1, or -1 plus 1 minus 1 gives -1, so that equals the charge. Okay, if the charge were 0, that is, if it's a neutral species, then those formal charges would have to add up to 0. Okay, the guidelines are in order of priority. Minimizing the formal charges is usually the most important factor. Matching formal charges to electronegativity is used as a tiebreaker. Okay, so the best structure here is structure 3. It minimizes formal charges. Molecular shape. For that, we have a very handy table that is similar to the one in the Chapter 8 lecture handout. And it is where the first column is the number of electron groups about the central atom. An electron group is a single bond. An electron group is a double bond. That counts as just one electron group, even though there's 4 electrons involved. An electron group is a triple bond. Again, one group of electrons, even though it involves 6 electrons. An electron group is also a lone pair of electrons. So we determine how many electron groups are on the central atom, and if it's 2, then the electron group geometry is linear, the bond angle is 180 degrees, and we have the molecular shape, which we call linear. If the number of groups of electrons about the central atom is 3, that could be a lone pair and 2 single bonds. It could be 3 single bonds. Then the electron group geometry is trigonal planar. So we have the atom in the center, and in a plane we have a triangular shape. The bond angles are 120 degrees. Now, if we have one of those groups of electrons being a lone pair as opposed to a bonded pair, then we call that molecular shape bent. If the group of electrons is 4, or rather the number of groups of electrons is 4, then we have the electron group geometry to be tetrahedral with bond angles of 109.5. So what we have is the central atom in the middle of a tetrahedron, and at the 4 corners of the tetrahedron we have then the groups of electrons. And if all groups of electrons are bonded groups, we call that shape tetrahedral. That's what we have, for example, with CH4. If one of those groups of electrons is a lone pair, then we have the molecular shape trigonal pyramid. We have that in NH3. If 2 groups of electrons are lone pairs, then we have the molecular shape we call bent. That's what we have in H2O, in water. If the number of groups of electrons is 5, then our electron group geometry is trigonal bipyramidal, and it looks like this diagram here. So we have a central atom, we have a plane about the central atom, a horizontal plane, which is a triangular shape where we would have 3 groups of electrons. We have a group above and we have a group below. So if you think about the bond angles, they are 120 degrees within that plane, and then 90 degrees for the one above to the plane, and the one below to the plane. If all of the groups of electrons are bonded electrons, that shape is trigonal bipyramidal. If one of them is a lone pair, then we have seesaw shape, so flip that 90 degrees and picture a seesaw. If two of those are lone pairs, we have T-shaped, so you see it looks like a T on its side. If three groups are lone pairs, we have linear. If we have 6 groups of electrons about the central atom, we have the octahedral electron geometry, where we have the central atom, we have a plane, a horizontal plane about it, which is square in shape, so we have 90-degree angles there. Then we have a group above, we have a group below, so all of the bond angles are 90 degrees. If one of those groups is a lone pair, then we call it square pyramid or square pyramidal. If two of them are lone pairs, we have square planar, which is a plane and the base is a square. So to figure out the molecular shape, you draw the Lewis structure, determine how many groups of electrons are on the central atom, how many lone pairs are on the central atom, and you use this table to decide the molecular shape. Now, polarity. Okay, so let's go back up here. For polarity, so what you do is you assign the most electronegative atom, whether it, well, those are the ones on the outside, so you give them the partial negative charge, where the one in the middle would have the partial positive charge. And if you can draw a plane, once you've drawn it showing the proper molecular shape, so you start with Lewis structure, you then draw the correct molecular shape. If you can draw, and you've assigned all the partial minuses, partial positives, if you can draw a plane, or you can kind of think of it as a line through the molecule such that you've got all the partial minuses on one side, all the partial positives on the other side, you will end up with a polar molecule. So let's go to the linear one. If the atoms on the outside have the partial positive, the one in the middle, if the one's on the outside, the partial negative, the one in the middle, the partial positive, you cannot draw only one line that separates all the partial positives on one side and all the partial negatives on the other. So, provided the molecule has the same element on the outsides and has linear structure, then it is nonpolar. But if we have two different atoms on the outside, it would be polar. Think of it as an uneven tug of war. Okay, so go to 3 groups of electrons. If it's trigonal planar, and we have the partial positive in the middle, the partial negative on each 3 of the attached atoms, then we cannot draw a plane that separates all the partial positives on one side and partial negatives on the other. So, provided all of the attached atoms are the same element in the trigonal planar molecular shape, it would be nonpolar. But if it's bent, then we can have the middle being partial positive, the 2 attached partial negative. Except for water, they're the opposite. We can draw a line through it between the middle and the attached that does separate all the partial positives from partial negatives. So when we have bent structure, it would be polar. In the case of 4 groups of electrons on the central atom, if all attached atoms, and there's 4 of them, are the same, and we have that tetrahedral molecular shape, that would be nonpolar. But as soon as one of them is a lone pair, we can draw a line from the putting the partial negative on one side and the partial positives on the other. So trigonal pyramidal would be polar, so would bent be polar. When we have 5 groups of electrons, if all attached atoms are the same in the trigonal bipyramidal molecular shape, it works out to be nonpolar. It's an even tug of war. But if we have a lone pair, seesaw, you could draw a line, a plane that separates the positives from the negatives. So seesaw would be polar. T-shaped would also be polar. Linear, however, you would not be able to draw a line. So linear, imagine you have the same atoms top and bottom, and they're the partial negative, middle partial positive. You would not be able to draw a single line to separate the positives from the negatives. So linear, provided the 2 attached atoms are the same element, would be nonpolar. So now we're at 6 groups of electrons. If all the attached atoms are the same, there's 6 of them, the molecular shape is octahedral, that's all balanced. That would be nonpolar. If there's 1 lone pair, that would become polar. If there's 2 lone pairs, so we have square planar, if all the attached atoms are the same element, that would be nonpolar. All right, so in our activity, we're doing part A, Lewis structures and molecular shape. We're doing part B, resonance and formal charge. We are not doing part C because it requires a computer program that's at the computers at Butte College, but I don't expect you to have that on your computer at home, so we are not doing part C. Okay, so you can ignore the pre-activity unless you want to get a little more practice. Don't submit it. Okay, so here's our report that we will submit. So this is Lewis structures and molecular shape. So for the molecules and ions shown in question 1, you're showing the Lewis structure. You are deciding on the electron group geometry, the molecular shape, use that table, the bond angle, that's from the table, polar or nonpolar, so we talked about that, and you're doing that for these molecules as well. And if there is resonance, do include the other, let's see, how do we do that? Complete the following table. Be sure to include all equivalent resonance structures of the molecules if applicable. So in drawing the Lewis structure, if there is another resonance structure or even more than just one other, draw all the resonance structures in that Lewis structure portion. And then you just look at one of those to decide about the molecular shape, the bond angle, and so forth. Okay, so you're continuing that same stuff with all of these molecules and ions. Part B is resonance and formal charge. Okay, so for that one, we have this molecule here, N2O. We're shown the 3 possible Lewis structures, and you are to assign the formal charge in each structure to each atom, and based on the rules that we talked about, we want the lowest overall formal charges distributed about the atoms. You decide which is the most likely Lewis structure. And in number 2, we have ClO3 minus ion, and we have those 4 different possible Lewis structures. And chlorine, being from row 3, it can have more than an octet. So that means structure number 3 and structure number 4, which have expanded octets, are possible for chlorine. So you assign formal charges to each of the atoms of each structure and decide which is the most likely structure. Question 3. Although chlorate, that's what we dealt with in problem 2, bromate and iodate, so those are equivalent. You just put bromine in where chlorine was or iodine in where chlorine was. They are common polyatomic anions. the fluorate anion. So if you put fluorine in the middle, which is hint hint from row 2, it is not known to exist. So in considering formal charges and resonance structures from question 2 and hint hint, the most likely one from question 2, and does it require an expanded octet? Can fluorine have an expanded octet being only from row 2? You should be able to answer question 3. Okay, and then we are skipping part C. All right, so that is it on the work that you need to do for this activity. So double check all your work, scan it, make it as a PDF file, and submit.